The topic for this lesson is the bipolar junction transistor, or BJT. A bipolar junction transistor is formed by using three doped semiconductor regions separated by two p-n junctions. The device is called a bipolar junction transistor because the current flow involves carriers of both polarities, both holes and electrons. A BJT can be fabricated either as a PNP transistor or as an NPN transistor, as shown in the illustrations. The central region is called the base. One of the junctions is forward biased and is called the emitter base junction. The other junction is reverse biased and is called the collector base junction. The three terminals are referred to as emitter, base, and collector terminals. The base region is lightly doped and very thin compared to the emitter region, which is heavily doped, and the collector region, which is moderately doped. The schematic symbols and current directions for the NPN and PNP bipolar transistors are shown in the diagram. The basic relationship for the currents is defined by the equation: the emitter current is equal to the base current plus the collector current. The biasing arrangements for NPN and PNP transistors are shown in the circuit diagram. These arrangements are instrumental for the transistors to work as amplifiers. In both cases, the base emitter junction is forward biased and the base collector junction is reverse biased. We recall that N-type semiconductors have extra electrons and P-type semiconductors have extra holes. Since the P-type semiconductor section in an NPN transistor is much thinner than either of the N-type sections, it logically has fewer holes than the N sections have spare electrons. The negative charge from the terminal connected to the emitter forces the extra electrons in the N-type emitter section towards the P-type base region. The base emitter PN junction is forward biased, so these electrons can cross over into the base section, filling the free holes. However, there are too many free electrons and not enough free holes. Since the base section now has more electrons than when it's in its normal state, it acquires an overall negative charge that forces the extra electrons out of the base region. These electrons cannot cross back over to the base emitter PN junction because of the strong negative charge being applied to the emitter section. Some electrons will leave the transistor through the base lead to the positive terminal of the base emitter circuit because the base lead is kept positive with respect to the emitter. However, this flow of base current is small. The collector lead is at an even more positive potential. The excess electrons are forced out of the N-type collector section into the positive terminal of the collector base circuit. Thus, this section of the semiconductor is left with a strong positive charge. Most of the extra electrons in the base region across the base collector PN junction are drawn out by this positive charge on the collector. The electrons jump the junction into the collector section and are drawn off into the positive terminal of the external voltage source. In short, we can say that the emitter emits electrons and the collector collects them. About 95% of the transistor's total flow will pass through the collector, whereas only 5% of the total current will leave through the base lead. Alpha is the term used to define the transistor's current gain between the emitter and the collector, where alpha is equal to the delta collector current divided by the delta emitter current. Alpha can also be defined in terms of DC, where alpha is equal to the collector current divided by the emitter current. Let's look at an example. Assume we have a transistor in which a 2.6 milliamp change in emitter current results in a 2.4 milliamp change in the collector current. What is alpha for this transistor? Alpha is equal to the change in collector current divided by the change in emitter current, or 2.4 divided by 2.6, which is equal to 0.92. A small change in the base current results in a large change in the collector current. The ratio between the base current and the collector current is called beta, where beta is equal to delta change in the collector current divided by delta change in the base current. Beta is also referred to as the current gain between the base and the collector. In our previous example, the 2.4 milliamp change in collector current could be achieved by a mere 0.2 milliamp change in the base current. Beta is therefore equal to the delta change in collector current divided by the delta change in base current, or 2.4 divided by 0.2, or 12. To find beta, if alpha is given, beta is equal to alpha divided by 1 minus alpha, and conversely, alpha is equal to beta divided by 1 plus beta. Using the circuit diagram shown, the following current and voltage analysis can be made. When the base emitter junction is forward biased, the junction acts like a diode. Thus, V sub BE is equal to 0.7 volts. The voltage across R sub B, V R sub B, is equal to V BB minus V BE. Therefore, VRB is equal to the base current times base resistance. Since base current times base resistance is equal to V sub BB minus V sub BE, and the base current is equal to V sub BB minus V sub BE divided by R sub B, the voltage drop across RC is collector current times collector resistance. Therefore, V sub CE is equal to V sub CC minus collector current times collector resistance. Collector current is therefore equal to beta times base current, and V sub CB is equal to V sub CE minus V sub BE. Using the circuit diagram shown, determine base current, collector current, emitter current, V sub BE, V sub CE, and V sub CB. The transistor has a DC beta value of 200. V sub BE is equal to 0.7 volts. The base current is equal to V sub BB minus V sub BE divided by R sub B, or 365 microamps. The collector current is equal to beta times the base current, or 73 milliamps. The emitter current is equal to the collector current plus the base current, or 73.4 milliamps. V sub CE is equal to V sub CC minus the collector current times the collector resistance, or 4.32 volts. V sub CB is equal to V sub CE minus V sub BE, or 3.62 volts. Since the collector is at a lower voltage than the base, the collector-base junction is reverse biased.